All right. I will begin with a word of prayer. So, Heavenly Father, we thank you again for your many blessings, and I just thank you that you died for us while we were still sinners. You had compassion on us and sent your Son to die for our sins. And we thank you for your grace and mercy to us each day. And I just pray you be with us. Help us to glorify you in what we do here this day. Lord, in your name I pray. Amen. So I have a worksheet to hand out to you guys. And so we'll be basically filling in this worksheet today. So if you just take one of these and pass it back and then to the next row. Yep. Was there something? Let me check. Probably. Can we call her?
Yeah, this is her ID.
Oh, I can give it to her. Well, that feels better, doesn't it?
Yeah.
Yeah. I was leaving church once, like last year, and I looked down, and I'm like, huh, that's the deacon's driver's license. Probably shouldn't be on the ground here. Like, he just fallen out of his pocket. Like, brought it back to his wife. She's like, oh, we've been looking everywhere. How on earth they drop it on the ground there, who knows? But anyway. Okay, so there's the worksheet. And here is an information sheet. Take one of these and pass it back. And I'll take and once you get to the end, make sure I get the extras, okay? All right, so before we get to this, I want to take a couple minutes here to show you this wonderful website called Desmos.com. Now, some of you have graphing calculators. That's lovely. But as you know, we don't allow graphing calculators on the test, right? And also don't allow computers on the test. Fine. But I'm not just about the test, right? I mean, the test it serves a purpose in here to try to make sure that you understand the material, right? But there are times when we want to use technology to graph things, and this is a pretty good resource, especially if you want to just take a look at formulas you have in another class, for example. Or if you just want to play around and see how graphing works. This is very, very helpful. Look at this. What we're looking at right now, I've graphed y equals x squared in green, y equals x to the 4th in kind of purple, and y equals x to the 10th in black. See how it works? And so I tried to do this by hand last class, right? But you can only do so good graphing by hand. We will be graphing by hand here today for the most part. But let's see here. Of course, I could also graph like y equals x to the, 50th power. What would that look like? See that in red? So as I was saying, the higher power you get, the more, if you're looking at this kind of scale, it just looks like goalposts, right? So that's kind of neat. But generically speaking, x squared is, mostly I just work, for the most part, we work in examples in here that it will be like x squared, all right? Let's see here, let's look at another one. So let me kill all this stuff here. How about this? All right, so 1 divided by x minus, or rather plus a. Huh? Oh, I forgot I got to click the button to make it show up. Let me fix my, let's try this again here. Add slider. All right, so this is, so in this Desmos, one of the really nice features about Desmos is that if you have like y equals some formula in x, you just throw a letter in there, it lets you add what's called a slider. And then you can adjust the value of the slider by moving this thing down here, and it will do things like, see, if a is positive, what's it doing? If a is positive, it's shifting to the left, right? See that? So here's 0 in the middle. Let me put a equals 0 as like a base case here. I'll put a different color. Here's just the reciprocal graph in the middle. See that? All right. And then I can move the other one by changing the slider. So if a is positive, right? If I add a value, it shifts the graph to the left, right? I mean, correct? If I make the a negative, it shifts the graph to the right. See that? Like that. Or if you want, we could animate it. And then if you really want to be silly, you could add a vertical shift. All right. Now I can move the graph up. Oops, let me put it in the frame here. Let me zoom out a bit so you can see better. So see, if I adjust the b, if I add a larger b, it moves it up. If I make b negative, it shifts it down. See that? Up and down. And then if I want to be really silly, I can animate both at the same time. I'm not sure what exactly the point of doing that is, but it's kind of amusing. If you want kind of like a low-tech screensaver or something, there you go. Yeah. What would happen if I made this a square in the bottom? What would that be? Let me turn this thing off here. As you can see, then it's the volcano graph, right? You can shift it up and down. You can move it left and right by changing the value of the slider. All right. What happens if I put a minus right there? It flips it upside down, right? So there's that. And of course, you can do other more fancy things, like let's try something else that's a little bit different. How about something like, oh, I don't know, y equals x cubed plus 3x minus 2x. All right, and then I'll add a constant. If I do plus b, what happens? Oop, sorry, caps lock. So that's a cubic, right? And if I adjust the b, it does what? It just shifts it up and down, right? What happens if I, instead of adding b, if I replace x with x plus b? What's going to happen then? Oops. Ah! Fingers. This keyboard's too small. What happens now if I adjust b? So now I've replaced the x with x plus b everywhere it appeared, right? So now if I adjust the slider, what's going to happen is the graph is going to go left and right, right? So if I add to b, if I add to x, I go to the left. If I subtract, I go to the right. See, there's a big difference between adjusting the input versus adjusting the output in terms of the left-right. Now, anyway, I just wanted to play around with this website for you for a second and point out that you can see all of the different transformations that I have on the sheet here, right? There's 8. I said there's 8 basic ones to look at here. You can add to shift up. You can subtract to shift down. You can adjust the input by subtraction to shift right, and you can, you have 1, 2, 3, 4 for shifts up and down and left and right, right? And then 5 and 6 are reflections over the x or y axis, and then we have stretches and compressions from 7 and 8. Now, let's just work some examples though, because I think I can write these things on a piece of paper and give it to you, but that doesn't make you understand it, does it? Let's see here. So we need to work some of these out. So we'll start at example 1 and just kind of work our way through. All right. Let's see here. So what's example now? In these examples, I've told you the order of operations that we can use to create the graphs. All right. In practice, a lot of times I wouldn't give that to you. You might have to figure it out for yourself, right? But to start with, I'm going to give you the transformations that you need in order to graph the thing, okay? So that's just to get us started. The truth of the matter is, this whole sheet, this whole exercise, really, it's like training wheels on a bike. Eventually, what you'd like is to not have to write down all these steps. You'd like to be able to do these steps in your head, right? Or a couple of them in your head at once, and just kind of like jump to the end point. That's what you'd like, because then you can graph with, you can graph pretty efficiently. But we have to start somewhere, so let's do that. All right, so what I'm going to do is I'm going to draw four like axes here, like this. And I'm going to go through the steps that I have in example 1, and then you guys can kind of write them down. Now, I'm probably going to have a problem on your quiz, which is like this worksheet, right? But all right, so let's get started. So what's step number 1? Oh, I guess I need to write the problem down, huh? So the problem is graph y equals minus the absolute value of x plus 3, close the absolute value, and then minus 2, I think it was. All right. So for a problem like this, I think if we track the vertex of the absolute value function, that's a pretty good way to do it. In the previous class, I tracked 3 points, and I think that was like, I don't know, I think it was too much. So our opening move here is to go, well, this is an absolute value graph, right? So I start with y equals absolute value of x. Right? This is one of the standard examples, which I reminded you on the sheet, right? Look at the list of 7 examples. It's one of those. This we should know by heart. It just basically looks like this, right? Step number 1. Then what I do is I shift 3 units to the right or to the left. We're doing to the x plus 3, right? So that means actually to the left 3 units. I know that's a little bit counterintuitive, but that's how it works. So because we're adjusting the input, x, rather than the output, we have to follow the rules for the transformations given in steps 3 and 4 on the sheet I gave you. So since I'm adding 3, that means I go 3 to the left. If you're not uncertain, double check it. To double check it, notice that when we plug in minus 3 into this formula, what do you get? What happens when we plug minus 3 into the absolute value of x plus 3? We get the absolute value of minus 3 plus 3, which is 0, right? So that shows you that this graph has an x-intercept of minus 3, which of course coincides with what I was telling you on the sheet. Now what's next? Next, I believe I said to reflect over the x-axis. So notice that the way this works is the transformation is not with respect, so understand this, guys, this is a very important point. The transformation is not with respect to the original one. The transformation is always with respect to the step right before it. So right here, if I go from this, I take the formula and I just multiply the whole formula by minus, that's a reflection over the x-axis. What does that mean? It turns it upside down, so the vertex stays right put where it was, right? Minus 3, 0. But it turns it upside down, like that, yeah. Now, I have purposefully not put tick marks or anything in this diagram I gave to you, right? It's like for sketching, right? I don't have like a fine grid on here, so this is really for the purpose of just getting a qualitative understanding of the graph, right? To be more quantitative, you'd have to add points, right? And then what? We're not quite to the finished product yet. We still need to subtract too. What does that do? Yeah, it shifts it down 2 units, right? So this vertex goes from minus 3, 0 down to minus 3, minus 2. And there you go. That's the graph that you're looking for. So we obtained it from a series of transformations. This is how we do it. Now I should warn you, I made a mistake in part. Example 2, like I was trying to work it out last class and I got halfway through and I'm like, I can't think of this, and the reason I couldn't think of it, it's wrong. So fortunately, I've already gone through that with them, so I'm going to correct your example 2 before it hurts us. All right? So, example 2. We're going to have to adjust the steps a little bit here, okay? Here we're trying to graph y equals the square root of 9 minus x minus 3. And I said it's helpful to rewrite it in that way, and I think actually it's not. Okay, so let me just not do that. So I'm going to follow a different order of steps, okay? So follow me here. Basically, if you want, you can just cross out the steps 1, 2, 3, and 4. Actually, steps 2 and 3 are the ones that are going to be wrong. We'll agree with what I have there on steps 1 and 4. Because however you slice it, what do you start with? However, when we're doing these transformation by graphing, right? What's step number 1? Step number 1 is always start with the standard example, right? So you have to identify which standard example is this. Is this the reciprocal graph? Is it the cube root? Is it the quadratic? It's what? Square root, right? Yeah. So we start with y equals square root of x. So there's my step number 1, right? So that looks like this, all right? And I'm going to track where the origin is. I'm going to track that 0, 0 point as we transform it, all right? Next thing I'm going to do is I'm going to flip that thing over. I'm going to flip it to y equals square root of minus x. What does that do? Yeah, it reflects it over the y-axis, okay? So this guy looks like this. All right? I'm trying to, so what am I trying? I'm trying to work my way to the formula at the start, right? So what would be would be a good move to do next? Oh, I guess I'm now starting to regret. I don't regret it that much, but this is minus what? X minus 9, right? Maybe my pre-processing is still relevant. Because with that kind of gives you an idea. Well, maybe if we do what? We want to take this function and do what? Shift 9 to the what? 9 to the right. So we shift 9 to right. That is y equals square root of minus x minus 9. So that shifts 9 right. So my vertex, my starting origin point, whatever you want to call that thing, it moves over to here. And again, these, this is a qualitative graph. It's not quite quantitative. I'm just, oh man, I was trying to do it in blue. I violated my color coding. Okay, this cannot stand. I'll fix it. All right. All right, now what? Finishing move, y equals square root of minus x minus 9 minus 3, right? So then we take this point, we shift it down 3. We're at 9 minus 3, and it looks something like that. I'm cheating a bit because I happen to know that this graph goes through. Again, you can take your qualitative graph and make it more quantitative by just paying attention to some details. In this case, I happen to know that the finished product has a point that goes through the origin, is what I'm trying to say. Do you see that? Look at the formula here that we're trying to graph. What happens when you plug in 0? Plug in 0 into that formula, what do you get? You get square root of 9 minus 0, which is square root of 9, right? minus 3. What is square root of 9? Square root of 9 is 3. 3 minus 3 is 0. Lo and behold, of course, the origin is a point on the graph. Anyway, so there you have it. This is the graph of that function. Now, an example like this is a little bit tougher than the first one, right? I mean, anytime you have this kind of reflection anytime you're reflecting across the y-axis, I find these kind of problems more challenging, right? I mean, personally, I do. You may disagree with me if you like.
If it was supposed to flip over the x-axis, would the negative be inside the parentheses?
If it was supposed to flip over the x-axis, the minus would be outside of the root.
Oh, so it would be outside of this.
Yeah, like, so for example, let me just talk about that. There's a big difference, right? So here's the big difference. If, and this is not in the problem, but suppose you were wanting to look at that. If you want down here, look at y equals minus the square root of x. What that does, instead of flipping it across the y-axis, it flips it across the x-axis like that. So, yeah. So this is reflect over y-axis. This is reflect over x-axis. I think the next example I have, I mean, there are problems that you can look at in multiple ways. Like this one, if you want to go, you can look, if you want to, you can go watch the video from the previous section. And in there, I show 2 different ways to graph this, actually. So like, there's not a unique set of steps. There's not a unique set of transformations that will graph it for you. There's many ways to do it. So I have just picked 3 ways. By no means are those unique, okay? So here, we're graphing y equals 3 plus 1 over 2 minus x. And I say it's helpful to point out that that's really 3 minus 1 over x minus 2 as a starting point. I believe that is an accurate statement. And okay, so let me draw my template. So I can follow, so you guys can follow along on your sheet there. What's our starting point? Y equals what? Yeah, exactly. This is a reciprocal problem, so we start with y equals 1 over x. For the reciprocal graph problem, you want to track the vertical and horizontal asymptotes. That's for best results. So the vertical asymptote and horizontal asymptotes here are literally the x and y axis for this guy. And I'm going to graph in red this time so you can see it better. So we start with this guy, right? That's on your list of standard examples. You need to know that, all right? Then what comes next is, I mean, there's various things you could do. But I think what I'm going to do is I'm going to shift, I'm going to create this thing, right? So I'm going to shift 2 to the right. If I shift 2 right, what happens is we move the vertical asymptote 2 units to the right, and the horizontal asymptote just stays put. All right, so that's y equals 1 over x minus 2. And it still looks more or less like a this, all right? Then what? Now I'm looking at my formula. I'm trying to work my way. My goal, right? My goal is to work to this formula through a series of steps, okay? And so I'm getting closer, right? But I got a minus out front, right? So I need to add that now. So we go y equals minus 1 over x minus 2. I'm going to put some parentheses in here for emphasis. What does that do? See, now this is like the red step, right? I'm multiplying the formula by a minus, right? I'm not replacing x with minus x. I'm multiplying the formula by minus. That's a reflection over the x-axis. What happens when you reflect over the x-axis? Well, think about the vertical and the horizontal asymptotes. The horizontal asymptote stays put, and Well, the vertical asymptote stays put as well. If you like flip this over, and it's just they're still where they were. So those don't move this time. But interesting thing happens. This flips up to here, and that flips down to there. Okay, so this is again reflect over x-axis. I'm always using the 8 steps that I gave you on this sheet, right? 1, 2, 3, 4, 5, 6, 7, 8, one of those. It's always one of those, okay? Next what? Now we got to add 3, right? So we do y equals, 3 minus 1 over x minus 2. And so what happens there is we're shifting up 3. So that is going to move your horizontal asymptote up 3. It leaves the vertical asymptote unfazed like that. So this is at 2. This is at 3 if you're keeping score. And basically it looks something like this. All right. And I've probably escaped the bounds of your I don't know, it depends on how you scaled things, but I mean, you try to stay in the box, but it's not written in stone. You have to stay in the box, okay? Like if you get outside the box, it's okay. It's just that's kind of a target for your graph, because I want to have a way to reasonably grade these kind of problems, and that's I wanted to give you, like, here's the format I'm thinking of trying, or maybe I'll have some common sense and give this as a multiple choice question so that I don't go crazy. I don't know, but anyway, does this make sense? All right, let's see here. Another way we could have done this one, right? Another way we could have done this one would have been as follows. What if we started here, right? And instead we went to what if instead we had started with y equals 1 over minus x? What would have that done? I mean, this is kind of silly in the sense that this is the funny thing about this particular graph, is that if you reflect the original graph over the x, or if you reflect the original graph over the y, what happens? It looks the same, yeah. So any way you slice it, you get this, right? So we could have done that, And then, I guess in terms of my thinking right now, it's something like this. Well, I guess I need a plus then if I do that. Yeah, that's another way to write that. And with that in mind, I could do, what would my next step be if I was thinking that way? So I could shift 2 to the right. Shifting 2 to the right. Looks like this here. Right. And then final blow. This goes up to here. Add 3. So this is a different set of transformations that also leads you to the end point. This was not on the sheet, right? But you could also think about this as a reflection across the y-axis followed by a right shift like that and that. Now, which is more natural to you? The way I did it to start with, or the weird way I did it I don't know, I'm sort of loading the question with putting weird there, aren't I? But, all right. Any question? Can I erase this? I want to go on to the next example. Example 4. Can I erase? Is it? Okay. So 4, there is a stretch. There's that factor of 2 there. And so anytime you've got like a multiplication, if you want to be careful, we should probably track some kind of points where we can, to really appreciate stretching or compressing, we really do need to keep some sense of scale. So in some sense, I don't like these examples for my worksheet because I really need like graph paper to fully appreciate them. But I'm going to do my best without having tick marks, okay? I'm going to do my best. So here we're looking at y equals to 2 times x minus 3 squared. Okay? So I start out with x squared, right? Y equals x squared. Now that, so here's, I'm going to try to track 3 points. I'm going to try to track the origin, and I'll use my best, I'll do my best here to put those points. Of course, I need to make that smaller. Sorry, I need to find something smaller. I need something. I guess I can use this. So roughly speaking, there. Okay, there's y equals x squared. These 3 points that I'm tracking, what are they? They're minus 1, 1, 0, 0, and 1, 1. All right, I'm going to track those 3 points. My next thing is to shift. I'm going to shift 3 to the right. Right? So I shift 3 to the right is my next move. And so that shifts each one of these 3 points to the right 3, right? So 0, 0 tracks over here to here-ish. 3, 0, right? And then the other one here, and the other one's there. So you guys tell me, what are the specific coordinates on the other 2 points there? What's this point right here, and that point is what? It's going to be 4, 1, right? And this one on the other side is 2, 1. So I'm getting those by just adding 3 to the x coordinates in each case. Shift 3 to the right. All right? And then what? And then here's where it gets interesting. Something we haven't done yet is we multiply the output by 2. So when you multiply the formula by 2, what it does is it stretches the graph vertically. So to get that, we just take the points that we're tracking, right, and multiply the y component by 2. So the 3, 0 stays put here, and so I'm still looking here, but now instead of being 1 unit up, I'm 2 units up. All right, and so it's going to look something more like this. If I could do it, I'm doing my best here, but if I had graph paper and I was tracking like 5 points, we could do better, right? But this point now is 4, 2, and over here you've got 2, 2. And there you go. So if I was doing better, you could see better that it was really getting more steeper vertically. Again, I think to be fair, to really do justice to the compression or stretching examples, we really do need graph paper, and probably you need to follow like maybe 5 points or so to really see it well. right. Next example. So I'm going to let you guys keep these, all right? So I might collect them some other days, but today I don't think I'm going to collect it. That said, this will count towards your participation, so like, you know, today is worth more than some other days since we did this. Okay, so we're graphing y equals x squared minus 6x minus 11. All right. So just to keep track of this day being worth more, let me just go ahead and top hat again for you guys. And I'll just kind of do that as a means of rewarding you for being here. You guys already top hatted once, right? All right, so I'm going to finish that one. Oh, that's unfortunate. Let's see here. So the next one is 6231. All right, so we're graphing x squared, y equals x squared minus 6x minus 11. How are we going to do that? Factor it out first. Sort of. How about we complete the square, right? So this is x minus 3 squared. And then that's going to be, what, minus... I meant to put a plus 11 here. Do you guys mind if I think I may have done algebra wrong on this sheet. Where'd my sheet gone to? Oh, look at that. I got a minus. So that should be plus 11. I was thinking plus 11, not minus 11 here. My bad. So just make that a plus 11 so this makes sense. So if I put a plus 11 here, that makes this work out to minus 2. Is that right? Wait, just a second. Sorry. Plus 2, actually. My bad. What's that?
So then for step 3 on example 5, it should be shift up 2?
Yeah, I think so. Yeah. So let's try that out here. So sorry about that, guys. Still working out the kinks on this formula sheet here. Do you like this formula sheet? Is this good? Do you like to do this kind of thing in class, or do you prefer me just to do examples? Sometimes I've created lists of examples for you guys. I don't always do that, but sometimes I think it's helpful. So here, y equals what? What's our starting point? This is a quadratic, right? So we start with y equals x squared. Yeah? So that's this guy. And then I'm going to shift right 3. So that just moves this over to here like so. Right, that's 3, 0. I'll just track the vertex. And then I shift up 2. And there you go, 3, 2. Sorry, not a little bit sketchy, right? What's the y-intercept? What's the y-intercept? See, we can combine this transformation graphing idea with other more basic things that we know, right? To make a better graph. What's the y-intercept? Remember, it's just whatever number appears here. Plug in 0, we get 11, right? So to be fussy, this would be at 11. So you can kind of gain a sense of the fact that my graph is not very much to scale, is it? Right? This is not really a good picture of it in the quantitative sense. Yep.
Is the auto on the same paper?
It is not. So I just changed this to plus 11. And when I change that to plus 11, that makes this become plus 2. So I changed it a little bit. Yeah, sorry about that. You're right, it is not the same as the one on the paper. If I did the one on the paper and I did the algebra correctly, we would have to shift down by 20. So it would be hard for me to put it on your little square thing, you know? So I'm trying to come up with examples where we don't move more than about 3 or 4 in any direction, so that I can so that it like plausibly fits in the little template that you have. And poor planning on my part. Example 6. What do we got for example 6? Absolute value again, huh? All right, so example 6, we're graphing y equals 1 plus the absolute value of 2x minus 3. All right, so this one here, we got to think about a little bit. This is annoying in a sense. So what we're going to do is we're factor that 2 out, and that gives us x minus 3 over 2, right? So we can factor, then the 2 comes outside of the absolute value. And once I write this formula, I look at this formula, I kind of know what I'm going to do once I have that formula. Because it kind of says to me, start with absolute value, all right? Shift 3/2 to the right, stretch by a factor of 2, you know, and then shift up 1. So to be fair, to do a good job here, I'll track 3 points again. So it starts out with absolute value, right? And I'm going to track 0, 0, and 1, 1, and minus 1, 1, right? Yep.
So you always want the coefficient x to be 1 when you're graphing the absolute value?
Well, this is the standard example. I start with one of the standard examples.
I mean, like, when you do it, you always want to have it be perfect like that.
Well, if I do make the coefficient 1, then I know what to do. You don't have to. I mean, there are other ways of seeing this. But
Is that what you think we should do?
that's, yeah, probably. I mean, this is a way to do it. Are there other ways? Perhaps. So next I'll do y equals absolute value of x minus 3/2. So that means I move 3/2 to the right, right? Like that. And I'm just going to write this one here, 3/2, 0. And then I do what? I stretch by a factor of 2. Oh, curses. What is that point? So it's 1 plus 3/2, which is what? 5/2, right? And minus 1 plus 3/2 is actually 1/2, yeah?
If you wanted to, would you be able to like stretch it horizontally by 2 and then vertically by 1?
Yes. Yeah, we could do that. That's a good question. And I think I would love to explore it if we have time. Let me keep writing, because we're about out. Let's see here, 2 absolute value of x minus 3/2. So I'm going to stretch vertically now. So these points become, you know, further up, right? Like that, right? Stretch by a factor of 2, and then finally we shift up 1, right? Finally we shift up 1. So our vertex is now at 3/2, 1, and we're like that, basically. I want to come back to the question that was just asked, though. The question was, could we do it by horizontally? Could we do it by horizontally compressing, right? So yeah, I think we could. So fine. I mean, we can do, you know, y equals absolute value of 2x like that, right? And so what that does is so multiplying by 2 compresses it, right? Of course, you can look at it 2 different ways. You could also look at this as 2 times absolute value of x. So you can also think of that as so horizontally compressing and vertically stretching are the same thing to the V graph. And then the question, though, is how do you go from here, right? How do you go from absolute value of 2x to the next step, right? See, because the input here is x. So what you have to do is think, well, I'm going to go y equals apps value of 2 times x minus 3 halves. You have to think like that, yeah? So then that shifts like this, right? And then you shift up by 1 and you're to the answer again. So does that?
Yeah.
Yeah. So anyway, next time we will be going on to other ways of graphing. So
So save the paper.
what's that?
We save the paper.
Yeah, the paper is yours. Yep.